This is Kenji Fuji speaking. This time I would like to make a presentation entitled Preliminary Evaluation of Seismic Capacity and Torsional Irregularity of Uto City Hall Damaged in 2016 Kumamoto Earthquake. So let us start from introduction. The main building of Uto City Hall was severely damaged in 2016 Kumamoto Earthquake. The most of structural damage was concentrated in upper stories, especially on the south and west elevations. From this point, the following questions arise. The first question is, has this building structure had enough seismic capacity to withstand against severe earthquake? The second is, why the most of structural damage was concentrated to the upper stories? The third is, from the damage observation, torsional response might be significant. Has this building been sensitive to torsional response? So, in this presentation, the seismic capacity and torsional irregularity of the main building of Uto City Hall are evaluated by simple method based on the structural design. I would like to explain the basic information of this building. This is the structural plan of this building. As you see, the structure of this building can be divided into two structural blocks, that is, office block and stair block. Two blocks are connected by only the concrete slab. In other words, there are no beams. As you see, all of structural walls are concentrated in stair block, while in the office block, columns are the only vertical members to resist lateral loads. This is a section of columns. This column A1B1 is the corner column in the office block. And this column A2B2 is the inner column in the office block. As you see, the sectional area of column is drastically reduced from lower stories to upper stories. This is very common in the reinforced concrete building constructed before 1981 because at that time the design seismic force in upper stories is smaller than that in current seismic design code of Japan. So, I would like to explain the preliminary seismic capacity evaluation based on structural design. This simplified evaluation method has been proposed by late Dr. Shiga, Professor Emeritus of Tohoku University in 1970s. First of all, I would like to define three parameters: wall area index, column area index, and average shear stress. Wall area index alpha Wi and column area index alpha Ci is defined by these equations. In these equations, AWI and HCI is the sum of sectional wall area of walls and columns respectively, and AFJ is the area of floor. Coefficient AI expresses the distribution of story shear force in current seismic design code of Japan. This figure shows the definition of sectional area. Note that for the calculation of wall sectional area, column sections are neglected. Next, I would like to define the average shear stress in walls and columns. So, two assumptions are introduced. The first is the weight per unit floor is 10 kN per square meters. The second is the base shear coefficient is 1.0. So, the average shear stress in each story can be calculated by these equations. This figure is so-called Shiga map. The horizontal axis is wall area index. The vertical axis is average shear stress. And these curves expresses the constant column area index. Based on the investigation of buildings damaged in 1968 Tokachi-oki earthquake, Dr. Shiga concluded this map can be divided into 3 zones. It is assumed that the average ultimate shear stress of wall is 3.3 MPa and that of column is 1.2 MPa. In Zone C, the sectional area of walls and columns are enough to withstand against assumed seismic force, while in Zone A, the sectional area of walls and columns are insufficient to withstand against assumed seismic force. I would like to explain the evaluation case. As I showed to you, 2 structural blocks of this building are connected only by slab. The border stop connecting 2 blocks at 4th and 5th floors are severely damaged. So, in this study, 2 evaluation cases are considered. In case 1, the evaluation is carried out as a single building. And in case 2, the evaluation is carried out as 2 independent buildings. What I am showing to you is the evaluation results of case 1, the case where the building is evaluated as a single building. The plots of y direction in the first and second stories are within Zone A, while the plots of upper stories are in Zone B and C. Therefore, it may be concluded that the seismic capacity of this building is insufficient to survive strong earthquake. However, this result cannot explain the fact that most of damage in this building are in upper stories. Next figure shows the results of case 2. The plots of office block in all stories are within Zone A, while the plots of stair block in all stories are within Zone C. Therefore, it may be concluded that the seismic capacity of the office block is insufficient, while that of stair block is sufficient if these 2 blocks of this building behave as 2 independent buildings. However, this result cannot explain the fact that the walls of stair block in the 5th story is severely damaged. So next, I would like to explain the evaluation of torsional irregularity. The parameters to be calculated are eccentricity ratio, ratio of gyration of story torsional stiffness, and eccentricity index. So the evaluation of story stiffness distribution is based on the sectional area of columns and walls, while the estimation of radius of gyration of mass above the story is based on the mass and mass moment of inertia above the story. This figure shows the distribution of evaluated torsional parameters. As shown here, eccentricity ratio in y direction is relatively large, and the radius ratio of gyration of story torsional stiffness with respect to center of stiffness are smaller than 1, except y direction in the first story. The eccentricity index in x direction is larger than 0.15 in all stories. Therefore, it can be concluded that this building is sensitive to torsional response. This building is classified as torsionally flexible system in all stories in x direction and second to 5th stories in y direction. So I would like to move to the discussions and conclusions. In this presentation, the seismic capacity and torsional irregularity of main building of Uto City Hall are evaluated by simple method based on structural design. The main findings are as follows. The seismic capacity of this building is insufficient to survive strong earthquake. However, the evaluated results of both cases cannot explain the damage observed in upper stories, and the eccentricity index of this building is larger than 0.15 in all stories in x directions. And this building is classified as torsional flexible system in all stories in x direction. Therefore, it may be concluded that this building is sensitive to torsional response. This is the end of the presentation. Thank you very much.